Today we're going to go over linear regression and also kind of a little bit of manipulating data. We'll go over some of the math and also some of the some code. We'll be going over some Python again. So let's get started. Okay, so working with data. So the whole thing with machine learning is you essentially process data as inputs and outputs. So it's like a function in math or like a graph where you have an x and a y. So you want to map an input data x to output y. So usually it must have like a one-to-one relationship. So if you look on the little picture on the right, it's mapping like x to y's, which are like one-to-one. So you feed it an input x and get an output y. So basically you're mapping data from x to y with each input x process. Like you can think of like the arrows to the right as basically processing it with a model to get an output or prediction y. So that's kind of the machine learning pipeline with data. We talked a little bit about it last time. Okay, so data set cleaning. So when you get data sets, a lot of times it comes with a lot more information than you actually want. So if you guys remember how last time we talked about matrices, you can think of like data set as having variables. Remember we mentioned like the columns as variables. So sometimes you have way more columns than you actually need. So you only want to subset and target specific columns to use in your models and machine learning processes. So yeah, you can delete columns, subset columns, and only focus on the desired traits and move. And another issue that you often have is, say you're sampling from a population, you're looking at samples from a group. There might be samples in there that just are extraneous or like essentially they're unusable. They're too different and they don't really match the actual population or like samples that you want to study. So you can also remove extraneous or problematic samples. Any questions about data set cleaning? That's like a pretty we'll go over like practical examples of that soon. Okay, so what is linear regression? So linear regression is the most basic, like pretty much the most basic linear learning method. You basically fit a line to a set of data, right? So you guys know the equation y equals mx plus b. Linear regression is basically fitting y equals mx plus b to data. So that's why it's called linear, because it's a line. It's linear. It's a linear model. It's the most simple. So what you guys have worked with probably so far is mapping y equals mx plus b, where x is a number and then y is another number. But with machine learning, what we're about to get into is how you can expand that, where x can actually be a vector or variable inputs and y is an output prediction number. So as you can see on the figure on the right, that's kind of like linear regression. You're basically fitting a line to the data points. Yeah, okay. All right, so the idea of linear regression. So basically it's, fit the most basic function y equals mx plus b to data. Y is the prediction, x is the input, and you're training weights with the bias b, right? So if m is what you're multiplying x by, m would be the weights, right? And then b is kind of to shift things up and down. You guys learned in and I'm sure you learned in like pre-algebra, algebra, that basically like sometimes graphs start out higher, and that's what the plus thing is. So this is saying like if all predictions have like a baseline or a minimum value, that might be the bias, right? You shift everything up because not everything goes to the origin or zero. So that's what the point of a bias is. It's called a bias, B-I-A-S. And then you have the weights, right? So yeah, as you can see here, y equals b naught, which is the bias or constant, plus the coefficient or weights multiplied by the variables, the inputs, right? So if we look to the data on the right, what you can see is there's like a function of, what is this? Yeah, so this is basically a linear function fitting a line to data, right? So that's kind of the idea of linear regression. So then what we're going to get into is something called multivariate linear regression. So this is linear regression, but instead of just having a single x number to number y, you input a vector or like a list of values that you then map to a single y. So this utilizes matrix multiplication or the dot product, which we went over last time. So an example is if you look, like there's multiple input values. Kind of ignore the graph. This is kind of not really that helpful, but it just kind of demonstrates again like the linear regression. But basically you're inputting multiple values multiplied by multiple weights and you get a single output. So I'm going to go into that a little more in depth now. So the matrix multiplication and multivariate linear regression. So the input is a vector starting with 1 then x1, x2, all the way to up to xn, or however many input variables you have. The weights are B, the bias, and then W1, W2, however many you have until Wn. So the way that you build this model is you dot the row X with the column W, and you get B plus X1 times W1 plus X2 times W2, that should be times, plus Xn times Wn. Sorry, I screwed up in the presentation. Does that make sense? If you guys look to the, if you look to the example below, remember how we explained when you dot, it's the row multiplied by the column. So if the column are the weights, you're multiplying each element in the variable multiplied by the weights. Yeah, so that's how you build the y's, which are essentially the predictions. So yeah, so each prediction is the input row, or x or 0, 1, x1, x2, all the way up to xn, multiplied by the weights, which starts with the bias and then the rest of the weights. So in most cases, weights are randomly initialized. So at first, the predictions are pretty off. What's a weight? A weight is essentially, you can think of it as like a coefficient, basically. It's like, so it's like these betas. Well, you can either refer to them as betas or W's. Essentially, it's how much you can think of it as like how much to pay attention to or how much to value this input, right? So if you have a function, it's like 1 times weight 1, then the weight 1 tells you how much to scale up or scale down a value, right? So basically you can think of it as, well, because when you're building the predictions, right, you have to multiply each of the different inputs by a different number. So the way to think about the prediction, the weights, is like if you have inputs, for instance, like you want to predict, so what we'll be doing later is housing prices. So if you want to predict housing prices, the inputs might be like number of bedrooms, number of bathrooms, square footage, etc. Basically what a weight says is how important is this input. If the input's more important, you have a higher weight, or the weight basically says pay more attention to this. Or if it's not that important, then the weight basically kind of minimizes and says, okay, we don't really care about this input. Like let's just ignore it, right? So it's called a weight because it like weighs how much to value this input value. Does that make sense? So it's like if we look at this, what these betas do is basically say how much should we care about each input, right? So if x1, if this column right here, x1, x2, x3 is really important, we'll be like, whoa, okay, we'll have a high beta for that column, or etc. Like it's basically like how much do we value this input? If each of these is a different input. Do you understand that? That's kind of what a weight is. It weighs the inputs and like how much they affect the output essentially. Okay, so we're gonna get into a little. So like I said, with linear regression, usually you just randomly initialize the weights, or just zero them off. But they basically don't worry too much about the technicalities. Just try to understand the general concept of what's going on here. So basically, what happens with machine learning in general is you can't just build a perfect model from the start, right? You can't just create a model and just initially be like, oh, okay, we have a perfect model. No, you have to tune it and essentially like train it. The word is train. You train a model to fit data, right? So when you start with a model, usually you randomize the weights, right? If you randomly initialize them, there's very small chance your random initializations are a good model, right? So it's, at first it's pretty off. So the way that you assess the accuracy of a machine learning model is usually with something called a cost function, okay? So what this cost function does is, if you look here, the notation might be really confusing to you guys, but basically what this does is says how far off is our prediction from the actual data. Does that make sense? So if you look here, it's yi minus the prediction, which is mxi plus b squared. So it's the mean squared error, which basically means you square the difference and you sum that up and divide it by the number of samples there are. So that's called the cost function. And what that does is it gives you a value of the quote unquote error of your predictions. Does that make sense? It's like how far off are your predictions from the actual? Yeah, so the whole point of this equation is to tell you the error of your model, like how far off is the model, right? Okay, so now we're gonna go into something that's probably very foreign for you guys. Don't worry about this, like don't worry about this because this involves calculus. But basically what you can then do is, using that previous equation, you can take something called a derivative. Don't worry about it, it's a calculus thing. It basically tells you how much, or like what's the direction to move to get a lower error. and you can just basically calculate that and then adjust your model using the error, using the derivative of the error. Once again, this is calculus and pre-calc. Do not worry about it. Just understand that you can use the equation to basically find how much you should adjust the weights by to get a better model. Okay, so the analysis pipeline, here, why don't I draw this? Okay, so you take like data, say like data, you feed it to the model, right? Sorry, my handwriting sucks. With weights, so say W is the weights, then you get predictions, let's call it Y hat. So you get a prediction, and then you put it into the cost function, and then you get the error, right? Okay, so then you have error. And then using this error, you can do gradient descent and then find out how much to adjust. So then you adjust these weights. And then you just keep doing this. Like you just keep doing this over and over and over and over again until you reach the minimum or like the best model you can get, or you like surpass the threshold of error. Does that make sense? So you just keep running this over and over again. You feed forward the model, you get a prediction, you find how much it's wrong by, you adjust the weights, and you run it back again. So that's why it's called descent, because you keep descending down towards the best solution. All right.
So is it kind of like guess checking?
It's not necessarily like guess and check. At first, it's guess and check, right? You first make a guess, and then
you use those errors to
so then you
make
use
your answer more precise.
Yeah, and then you make it more precise. But after the first guess, you can just keep working towards the correct part, right? So it's not like every single time it's a guess and check. It's at first it's a guess, and then you check, and then you keep checking, right? So it's basically like you're taking small steps towards the ultimate goal. At first, it's for instance, it's like you randomly start in the middle of nowhere, but you have a compass, and it's like, okay, let's just keep heading north. So then you keep heading north, and you basically check your progress every once in a while, but you're just heading in the right direction. That's what matters, right? So you start off somewhere random, and you just head in the right direction. So that's essentially what this is. The right direction is a better model. So you start randomly with a random model with random weights, and you just slowly work towards the best model. So that's the whole idea of this. And this is done using cyclical process and like calculus and stuff like that. Yeah. So do you guys understand? That's the whole basis of like, this is a very simplistic version, but the most complicated machine learning models also kind of use this. It's like you start randomly and you work towards the best model. Even really complicated models kind of use this idea. So another thing that you can do is essentially data normalization. So this is like cleaning method that performed on like your input data. So if we go back to the multivariate linear regression, if you think about it, you're having multiple inputs, right? So you're having multiple variables that the model's taking into account. So what data normalization does, this is mostly important for like large data sets and big analysis. So it's not that important for linear regression. But essentially, you don't want the data set to have huge differences in scales of data. So what that means is, for instance, if you're building a model that has like, let's say, like, okay, if we go back to housing prices, right? So you want to predict the housing price, but the inputs are number of bathrooms. How many bathrooms can you have? Maybe it's from 1 to the very extreme, like 10, and that's extreme, right? But then if you think about square footage is on a completely different scale. Square footage goes from maybe tiny, like 100, 200, up to like huge mansions with like 10,000, 20,000, right? That's a completely different scale. That's in the tens of thousands, whereas bathrooms is from 1 to 10. So basically what this deals with data scaling. So what you can basically do is you can scale data. Once again, this is statistics. Don't worry about the math of it. Just understand the concept. You can scale the data to be between much smaller ranges. So you can scale the data so it's between the range of like maybe mostly -1 to 1. But very extreme values might be like 2 or 3. So this is basically done using statistics and like normal distribution and all this other stuff that you guys don't have to worry about. But just understand you can take numbers with completely different scales, like 0 to 1. Like even maybe there's even data that's 0 to 1. Like maybe it's a percentage or something like that. But what you can do is you can take all these data that have completely different scales and then rescale them. So because like if you think about it, if you randomize weights, right, and you have a weight that say they're all randomized to 1, regardless of what the weights are, the huge scaled numbers are going to be weighed way more heavily because they're huge compared to the tiny ones. So basically, you want to scale back data so they're all kind of represented equally, and then that way it kind of trains quicker. Because if the huge numbers aren't important, it's gonna you're gonna have to like make the weights tinier like a lot of times to be able to scale it down. So basically, this just helps with initializing the models to kind of be reasonable, and then scale them to basically fit the best model. So it's just like data scaling, because you don't want everything to be on completely different scales because it gets really jank. Okay, so another thing is called the training and the test set. So basically what you do is, I'm gonna go over a concept with you guys. It's called overfitting. So what overfitting means is when you have a model and you train it on some data. What overfitting is when the model is overfit, or it performs well on the training set or the data that the model was trained on, but it doesn't perform well for like other real world data, right? So if we think about it, because if you're trained to only, so you can think about it in like humans, for instance. Like if we're only trained to like drive in like one specific street or area, if you suddenly throw us to the rest of the world, we're probably going to suck at driving because we don't know like the rest of the world. We don't know all these other things. If you're trained to do a task, or if you're trained to do math and with like one single question, you can do that one question. You can do that one question really well, but suddenly you won't be able to perform well on like everything else because it's like it might be foreign, it might have different patterns or stuff like that. So that's what overfitting it means. It means you overfit the model to perform well on what it was trained on, and that's not good because the whole point of machine learning is you want to train a model, but then you want that model to perform well for real world tasks because you want to be able to use it in the future to do real world things. So what people often do is they split the data. So first off, this has to do with like data distribution. Like, is the data matched like the real world application? Like, is the data like distributed or like has the same like distributions as like the real population, etc. That's that's a little different. But basically what you can do is you can split the data into a training set and a test set. So the training set is what you train your model on. The test set, you then test the model on it, right? So if it does well on the training set, but it fails on the test set, that means you overfit the model because the model only performs well on the training set. But if it performs well on the training set and the test set, then it's more promising because they're like, okay, so this model wasn't trained on the test set, but it performs well on it, which means that it can predict something that it wasn't trained on. So that's promising for using real world applications of a model. Now we're just gonna go head first into some Python. Okay, so yeah, we're gonna use Python packages to load in some Boston housing price data, and then we're gonna use multivariate linear regression to fit it and predict it. So once again, you can see I annotated this, so it kind of explains what I'm doing. So once again, like last time, so this is last time's code, numpy, however it's pronounced. We're gonna use a different. Do we have to open? No, you don't have to open Python. I'm just gonna kind of show it. If you guys aren't familiar with code, doesn't matter. This is just kind of showing that it can be done and kind of like in general how you do it. But yeah, so basically what we're doing here is with Python, as I mentioned last time, we use the numpy package. Here we're using the pandas package, which is also a data package, and also all these other packages, which are also data analysis statistics packages. So you can see that you just import the packages. And what we're doing here is we're loading in a data set. So here we go. Okay, so we loaded in a data set. So you see load, that loads in the data set. This pd.dataFrame basically sets the data set as a data frame, which is a sort of data set. It's basically like an array, but a little different. And then here, we're doing, do you guys remember the bracket? This is a different package, so the notation is a little different, but it's pretty similar still. What the bracket does, once again, is like indexes into an array, right? So we're indexing into the Boston array. So if you look here, we're indexing into Boston, and then we're setting this MEDV. We're setting the column MEDV equal to the target from this data set. So that's what this command does. And then I don't, if you guys are familiar with code, you guys will know things about like nulls or NA, which basically means empty or there's no data here. So we're saying check if it's null and then sum them up. So what we see here is there's 0 nulls. That's good. That means all of our data is present. So what we're then going to do is we're going to set X equal to Boston. So we're going to create X as the Boston data. So we're going to take the data from Boston and create it as X for the inputs. Then we're going to take the housing prices, which is MEDV, the column MEDV, and set that as Y. However, you don't want the predictions in the X data set. So then what we're doing here is drop. We're going to drop the column MEDV because that's just the prediction column, and we don't need that in our training set or X. So now we have X and Y. See, they have the same number. They're 1-to-1, 506, 506, 506 samples. And once again, if we look here, right? So the rows are the index or the sample, right? So each of these rows is a different house. And then each of these columns are a different variable that kind of describes the house, right? So each of these is a different factor that kind of tells us something about the house. And then Y is just the predictions, and these are the housing prices. So what we're then going to do is right here is we're going to normalize it. All right, we're going to do something called z-scoring. So essentially what this does is if some, so you guys know what average is, right? Mean is, everyone knows what a mean is. It's like the average of the data. So what we're doing here is we're going to basically scale everything so that if you're closer to the average, you're closer to 0. If you're farther from the average, you have a higher number. So this is called z-scoring. So essentially, so say you're like really, if you're like right at the average. So say you're like with height, right? If the average height is, I don't even know what the average height is, maybe 5'6". If you're 5'6", your value is gonna be set to 0. But if you're like maybe 3 feet tall, your value is gonna be set to like a negative number. That's like, I don't know exactly off the top of my head the distribution, but you're gonna be set to a negative number. That might be large. And if you're really tall, if you're 7 feet tall, you're set to a large positive number. But by large, I'm still talking about like max, maybe like it can get large, but most of the data stays between the range of -3 and +3, and the majority of it is distributed around 0. So it's just something called z-scoring, which has to do with statistics. But yeah, so basically you're scaling the data. So regardless of what the original distribution of the data is, say it was maybe like 100,000 to 100 million, you're basically bringing it within a small distribution and scale. So that's what this does. So we're looping through each column. Oh, but the reason we're looping by column is because you don't want to z-score data with like with other types of data within, like you want to z-score it with itself. So you want to distribute and normalize the data across its own variable. Like you don't want to normalize like number of toilets with square footage. That doesn't make sense. They're on different scales. So you only normalize it by its own like column or by its own variable, which is why you do it per column. So that's what we're doing here. Okay. So then, yeah, so then what I'm doing here is we're splitting the data into an 80%, 20% training set and test set. So you can see X train, X test, Y train, Y test, and then it just uses this package that does it. And 0.2 means that 80% training, 20% test. So that's what we do right here. So now you see over here, we have the X test, X train. Look at it again. Same number of variables, except this time it's the training and test set are it's either randomly distributed. Sometimes it's random. Sometimes you do it to maintain the same distribution of data. But yeah, so you can see 80% to 20%, 400, 402, 80, 20. Same with the Y train, Y test. Once again, 1-to-1. That makes sense. Let's see what the question is. So then, yeah, so then we're going to import the package linear regression. And then we're going to do something. This is why coding languages are so nice, because you don't have to actually, a lot of times you don't actually have to write out the function itself. Like you don't need to write out the entire linear regression function, right? Because that requires math, that requires manipulating matrices and all this stuff. But a lot of times with programming languages, a lot of stuff is written already. So we can just, it's that simple. We can build a linear regression model by just calling the function linear regression. So we call the function linear regression, and we do fit on the data we want, X train, Y train. So we just fit it on our input and output data. So once again, like I mentioned earlier, you train the model on the training data, right? Because you want to fit it onto a subset of the data. So now what we're going to do is we're going to see how the model performed on the training data. So if we look at the train, and then basically how I'm checking how it performs is I'm doing a Pearson correlation test, which is just a correlation test is basically just looking at how like do things match together. Like if something is high, if like a value is 1, is the output also 1? Basically it's like checking how like close together the inputs and outputs resemble each other. So we see a correlation of 0.86 essentially for the training set, which is pretty good. It's not ideal, but depending on the type of analysis you're doing, different types of correlations are good. And then we can see for the test set, which is the data we did not train the model on, it actually performs better at 0.867 essentially. So that's pretty good. That means our model performs really good on the training set and the test set. So we can then visualize this using scatter plots. And as you see, okay, so this is a training set. You guys kind of understand what we're looking at here? So the x-axis are the predicted values and the y-axis is the actual. So we see that the training set correlation is equal to 0.86, and we see that this is what the predicted versus actual looks like. So this is what our model predicts. And then we can look at the test set using this command, and we see this. So this is what the test set looks like with prediction and actual. Does that make sense? So each of these dots is a different sample, and the dot's x value is its predicted value. The y value is its actual value. So if this data was, if the model was perfect, this wouldn't look like this distribution. Instead, it would just be a line. You just see a line of dots without along y equals 1. But because it's not perfect and it's kind of a variance in the predictions, you see the data looks like this. It's like it's a jumble of dots that pretty much resemble the line y equals 1, but obviously there's variance along it because the predictions aren't perfect.
Is there any way you can get like a perfect model?
Yeah, yes and no. If you wanted like overfit, there's but like the other thing is like you try to not overfit. So sometimes you sacrifice like training set prediction for like test set or validation set or test set accuracy. So sometimes the correlation might not be as high on the training set, but necessarily a perfect model, I don't like, not really. Like oftentimes there you can get very close. Like you might get like I've had models that have like correlation 0.99 or even correlation 1, but that doesn't mean that every single prediction is 100% accurate. That just means like on the population scale, the correlation of all the different points together is incredibly high, which means on a population scale across all the data, it performs incredibly well. But that's not always the case. Like even if you have an incredibly accurate model, there are still always outliers, right? So some things just don't follow the same patterns, right? Because the whole point of this is it's picking up the patterns. We're looking at the patterns of the variables that help us predict the outputs, right? But not everything follows the patterns. In general, with like data and even a population, right? Like in general, people follow patterns. So with housing prices, there's the common things that are likely going to attribute to how much someone pays for a house, right? Like someone won't just buy like a box for like $1 million because that doesn't make sense. It's like that's not a good house. It's missing tons of things. But people generally with like more bathrooms, more square footage, better location, they'll generally pay higher. So that's a pattern. That's a pattern that you identify in like housing prices. So the whole thing is that if you generally, the whole thing with machine learning is you find the patterns in data that help you predict the outputs. But like I was just saying, not everything follows those patterns. The whole thing with like population, like is like in general, most things follow the pattern, which is why you're able to find like on a population scale, like almost perfect models with like 0.99 or correlations of 1. But there's still always going to be outliers or things that just don't follow the same patterns. And you'll get like extraneous outputs or like extraneous data with those. So yes, you can have very, very, very strong models, but you can't always expect to just get like a perfect prediction every time. Does that make sense? That kind of also goes into that whole idea of like what it actually is like machine learning looking for.
Yeah. So like it's a possibility, but there every single time there's gotta be some extraneous values.
Yeah. Yeah, so that also goes back to what I was saying with like data cleaning. it's like if you find values that are like really weird or just completely different from the rest of it, sometimes you just get rid of them because like you don't really want those to affect your model. Because if we suddenly like if you look at this test set, right? So you see most of it's like not. I don't think there's like really an extraneous value here. They like all pretty much follow
Yeah.
the same distribution. But if we suddenly had a point at like or actually no, this isn't a good example because this is wide predictive versus right training. But if we here, let's go into the X. Okay, so if we look at X, right? This is already scaled, but say we suddenly had some point that was just completely different. Like it had like a super low like a super low price, but suddenly like all the other things pointed to it being like a high priced house. Like if it's completely different from the rest of the data, then we might want to drop it because that probably negatively affects our model and causes us to have completely different. It would basically scale the weights or affect the model differently from all the rest of the data, which follows a pretty similar pattern. So that's kind of one of the things, which is you don't want super extreme points or like cases that will negatively affect the model. Like you, in general, you want like a population that's pretty similarly distributed, and like accurately represents what you want to study.
Is that why you like normalize the data?
Yeah, like I said, that's why you can't sometimes normalize it because you basically you want to scale everything together to build the best prediction. So it's not like artificially scaled up or down.